In the previous lecture, we studied a very simple example where there was a single aperiodic recurrent class, and we saw that the probabilities converge to values pi j that are independent of the starting state. If you recall the example, we had two states, and the transition probabilities were 0.5, 0.5 from state 1 to state back to 1 or 2. And from state 2, there were 0.2, 0.8. And we said, we observed that P ij of n's, the matrix of Pij of n's, which are given essentially by P to the n as n goes to infinity, this matrix converged to numbers that were independent of the starting state. So, and these were pi 1, pi 2, pi 1, pi 2. Okay, so pi ij's are pi j. Okay, pi ij being defined as the limit as n goes to infinity of Pij of n. Okay, so when does this convergence occur? Does it always occur? Now, we'll define the stationary distribution. The vector pi is called a stationary distribution of the Markov chain if pi has entries pi j, where j come from the state space, such that, first of all, pi j's are, of course, non-zero for all j. Non-negative. They're probabilities, and they sum to 1. And more importantly, the vector pi is a solution of the equation pi equals pi p, which is to say that pi j equals summation over all I pi I Pij for all j. Okay, so if a vector pi solves this equation, and if it is a probability vector that sums to 1, then we say it is a stationary distribution. Now, such a distribution is called stationary for the following reason. Consider pi p squared, for example. This is pi p times p. But pi p is pi, so this is pi. So then, consequently, pi times p to the n is pi for all n. This means as n increases, the vector of probabilities do not change. Hence, the name stationary distribution. Now, a theorem follows. An irreducible Markov chain has a stationary distribution pi if and only if all the states are non-null recurrent. Okay. And in this case, pi is the unique stationary distribution, and is given by pi I equals 1 over Ti bar, where Ti bar is the mean recurrence time of state I, which we defined a couple of lectures ago. Ti bar is the mean recurrence time. Clearly, if a state is null recurrent, then Ti bar is going to be infinite. Is going to be infinite. Hence, the steady state probability of that state is going to be 0. Okay, in the null recurrent case. I'm not going to present a proof of this theorem. You can find the proof of this theorem in your textbook or in any other related textbook. So I'll give a related theorem here that is going to be useful for us to solve this example again. Now, if the chain is irreducible, meaning there's a single recurrent class, and I mean irreducible, there's a single class and that is recurrent, then, so basically if the Markov chain is irreducible and recurrent, there exists a positive root of the equation x equals xp, which is unique up to a multiplicative constant. That is unique up to a multiplicative constant. Okay, so there is, in fact, these stochastic matrices, P is a stochastic matrix, and stochastic matrices have very unique, very interesting properties about their eigenvalues and eigenvectors. There is Perron-Frobenius theory, which is a study of these properties. And for our case, it is useful to know that this equation always has a positive root. And if we are looking for the root, which is the eigenvector, that adds that sum, whose elements sum to 1, then we find a unique probability vector that solves this equation, and that is going to be our stationary distribution. Now, the chain is non-null if summation xi is less than infinity, and null if summation xi is infinity. Now, how do we use this theorem? We use this theorem in solving pi equals pi p here. Pi equals pi p. We are going to find the vector pi that satisfies this equation, but in order for this vector to be uniquely determined, we need this to also be satisfied. We need this pi to be a probability vector. All right, let's try to solve this. Now, pi equals pi p is also known as the global balance equations. What does this mean? Now, let's write them down. Well, pi 1, pi 2 equals pi 1, pi 2 multiplied by p, which is in our case 0.5, 0.5, 0.2, 0.8. Okay, now this says that pi 1 is equal to 0.5 pi 1 plus 0.2 pi 2. right? And pi 2 is equal to 0.5 pi 1 plus 0.8 pi 2. So given that I am in state 1, with probability 0.5, I'm in state 1 again, and with probability 0.5, I'm in state 2. So what are different ways of being in state 1? Either I'm in state 1 and I stay in state 1, or I'm in state 2 and I switch to state 1. Okay, now at steady state, the probability of transitioning, the frequency of transitions out of a state must be equal to the number of transitions or the frequency of transitions into a state, by definition of steady state. So this equation, or these two equations, are therefore known as global balance equations. And this theorem tells us that they give us the unique stationary distribution. So when we try to solve this, we are going to find out that 2/7 and 5/7 satisfy these equations, but these two equations have just by themselves, these two equations are the same equations. They are linearly dependent. So we are going to need to use this, right? So from here, let's try to solve the first equation. The first equation says that pi 1 is equal to 2/5 pi 2. And the second equation says, again, pi 1 equals 2/5 pi 2. It is the same thing. So we are going to find the values pi 1 and pi 2 that satisfy this, that also add up to 1. So pi 1 plus pi 2 equals 1. What are those values? 2/7 and 5/7, which is the same thing that we found by taking n to infinity here. Okay, so to sum up, if we have an aperiodic Markov chain with a single recurrent class, we can solve pi equals pi p together with summation of pi I equals 1 to find the unique steady state probability vector. In the case of a Markov chain where the states are null recurrent, then these probabilities, if we can solve this, the probabilities would be 0, because the probabilities are also equal to 1 over the mean recurrence time. In the null recurrent case, the mean recurrence time is infinite.